Kia ora koutou. I wanted to go through some questions that were like the ones in exercise 11B to help students who haven't had a go at that exercise yet. So I've just picked out 5 questions. Some of them are exactly the same, and some of them I've just changed the numbers around a wee bit. And I'm just going to blast through them reasonably quickly. If you've got any other questions in that exercise, please let me know. And also note in the work solutions, there's a mistake in one of the questions. I'm pretty sure it is question 7, part 2. So have a look at that before you spend too much time trying to make that proof work. Okay, so let's go with question 1. We have to just do some complex number division. So the key here is to multiply the numerator and denominator by the conjugate. So it's fine not to put those in brackets, although I usually do, just so that, I don't know why I do, I just think it looks better. Doing the numerator second, so we'll start here. We've got 6 sixes are 36, minus 12i plus 12i, and then I've got minus 4i squared, so that's plus 4. So this is the minimal working I'd put down for this question. In the numerator, we've got 42 plus 30i plus 14i minus 10, right? Being careful here that we've got a plus 10i squared. So cleaning up and grouping the real and the imaginary bits gives me 32 plus 44i divided by 40, and we need to simplify our fractions, giving us 4/5 plus 11/10i. Just notice that I always write it in this order, in A plus IB order, or BI order. Okay, on to the next question, which is similar, but just has one extra little step. So just before we start multiplying out the denominator, we can see that we've got a common factor in here of 4, and we're going to end up with a common factor in here of 4 as well. So this is 12 minus 8i over 2 squared into 1 plus I squared. Dividing through everything by 4 gives me 3 minus 2i over 1 plus 2i, take away I squared, plus I squared, which is take away 1. So 3 minus 2i divided by 2i. So usually we multiply by the conjugate, but in this case, all we have to do to get ourselves back to our nice A plus BI pattern is just multiply numerator and denominator by I. That leaves me with negative 2, and then here we have 3i minus 2i squared. So that means, what am I doing? Oh no, I don't need to do all of this. Let's go back up. Okay, stupid brain. Okay, went too fast. I've got 3 minus 2i over 2i, which gives me 3 over 2i, take away 1. You could do all the stuff I was about to do, but we don't need to. Here, I'm going to multiply by I over I. So 3i over 2i squared minus 1, which gives us 3i over negative 2, take away 1. Rewriting that in the usual order, we get negative 1 minus 3 over 2i. Okay, so that's that question done. Let's see what's next. Okay, so find the square roots of negative 9 plus 40i. As usual with these, I start with letting z equal x plus iy. And we're going to work this one through in rectangular form, and as I've said in class, this is a kind of a set piece of complex numbers algebra. We're going to end up getting 2 solutions. So we let z equal x plus iy, and then we know that that number squared has to give me negative 9 plus 40i. Expanding that out, x squared plus 2xyi minus y squared is equal to negative 9 plus 40i. And back up here, we should notice that we require x and y to be real numbers. In other words, this is in my normal complex number form. Grouping the real and the imaginary parts, we get x squared minus y squared is equal to negative 9, and 2xy is equal to 40. So again, I'm using the idea of matching coefficients. That gives me xy is equal to 20, y is equal to 20 over x. We take that and we substitute it into here. x squared minus 20 over x all squared plus 9 is equal to 0. Multiplying through now by x squared, we have x to the power of 4 minus 400 plus 9x squared equals 0. So that's a quadratic. We've got u squared plus 9u minus 400 equals 0. And I'm looking for two numbers that multiply to give me this and have a gap of 9. So I don't know about you, some of you will spot that straight away, some of you won't. So if you don't, one way to do it is with a factor tree to get to your prime factorization. So just like you did back in year 9. So we're looking for the prime factors. We've got 2 and 5 here, and we've got 5 and 8, and then we've got 2, 2 and 2. So I want some combo of those that's going to have a gap of 9. Well, straight away you can see that 25 jumping out here, and here we've got 16. So that's what we want. So it factorizes easily. Now in the Cambridge exam, they usually will factorize easily, so just try that first before you leap to the quadratic formula, which is what you probably would do on that one if you didn't spot the factorization. So we've got u times u, we want to have a plus 25 and a minus 16. Okay, so u was equal to x squared. Either use x squared is equal to negative 25 or x squared is equal to 16. But x is real, so no solutions here. Here we get x is equal to negative 4 or x is equal to 4. Going back up, we had y is equal to 20 over x. So y is equal to 20 over negative 4, which is negative 5, or y is equal to 20 over 4, which is 5. So my two solutions to this one are z is equal to 4 plus 5i. That's from these ones here. Or z is equal to negative 4 minus 5i, which is just the negative of this first solution. Right, a couple of questions left. I think they get more proofy. Let's see what I've put here. Oh yeah, this next one is question 3. There are two ways to do this. And if you look in the work solutions, I've done it the way I'm going to do now, and then I've done a kind of messy matching the coefficients way. So you probably have figured out by now that I love the matching coefficients method for lots of things we do this year. But in this case, we could start out by letting z equal x plus iy, right? And I'll just show you what's going to happen, because it ends up being a bit of extra work. So if we do that, we have x plus iy minus 1 is equal to 10 minus 5i. From here, I can expand all of this, and then I can group up the real part and the imaginary part. And I get two simultaneous equations to solve, and we will get there. But it's just easier just to do what we would usually do and solve for z. And that's the method I'm going to do in here so that this video doesn't get disastrously long, because I know that you're going to stop watching. Right, so we started with whatever the equation was, 3 minus 4i times z minus 1 is equal to 10 minus 5i. 3z minus 4iz minus 3 plus 4i is equal to 10 minus 5i. Z into 3 minus 4i is equal to 13 plus 9i. So z falls out pretty quickly from here. 13 plus 9i over 3 minus 4i times by the conjugate, giving me denominator first, so 9 plus 16. Up the top we've got 39 plus 27i plus 52i minus 36. Is that right, or have I done something wrong? I've copied something wrong, I think. Yeah, I've done something wrong up here. Look. Okay, so always worth checking back. This is minus 5i here. So here we should have take away 9i. And here we should have take away 9i. Luckily, you're not going to be in class when you watch this, so you can't all yell to me that I have mucked it all up. You can just yell that down your laptops. Right, there we go. Let's fix all of these signs up and see what I've got to do. Okay, 39 minus 27i plus 52i minus 36i. No, minus 30, I'm really tired, sorry, minus 36i squared, which is just plus 36. That gives me 39 plus 36, 75 plus 25i divided by 25, which is a very lovely, well, kind of round number, except that it's complex. So we get an answer of 3 plus I. So have a look in the work solutions if you tried it the other way and see why it's worse. Right, 11 minutes. I've got a couple of minutes left to do these last two. So what's coming up? Oh, the next one is another solve one. And then the last one looks bad, but actually is easier than question 4. So with this one, we are going to start by letting z equal x plus iy, and then doing the obvious expanding from that point on. So we start like that. Expanding this gives me x squared minus y squared plus 2xyi equals 2x minus 2yi. Now, x squared minus y squared minus 2x equals 0, right? So what I'm doing here is I'm grouping the real bits, and then I'm grouping the imaginary bits. That's coming up in a second. So we're going to get simultaneous equations. 2xy equals negative 2y. I want to look at this one first because there's a really common mistake here, which is that it's fine to divide both sides through by 2. That gives me xy is equal to negative y. It's not fine to divide both sides through by y. What I'm going to do next is get it to be xy plus y equals 0. Now we factor out the y and we get y into x plus 1 is equal to 0. So from this equation, we get y is equal to 0 or y is equal to x is equal to negative 1. Just clean that up. X is equal to negative 1. Now we take this and we substitute it into here. And that should say x squared minus y squared. I don't know what that thing was, but there we are. Substituting that in gives me x squared minus 2x equals 0. So x is either equal to 0 or 2. So x equals 0 or x equals 2. My first two solutions then are z equals 0 plus 0i, which we just say is 0, or z is equal to 2 plus 0i, which is just z equals 2. Okay, so that's solution numbers 1 and 2. Next, we have to consider what happens when x is equal to negative 1. So we're going to take that and we're going to substitute that in there now. Negative 1 squared. Oh, we'll just turn off the ink to shape thing. So negative 1 squared minus y squared plus 2 equals 0. So this time we're saying, well, if x is negative 1, what must y be to give me a solution? And we get 3 equals y squared. So y is equal to plus or minus 3 when x is equal to negative 1. So we need to write that out nicely as my last two solutions. Z is equal to negative 1 plus root 3i, or z is equal to negative 1 minus root 3i. Right, so for that question, we end up with these 4 solutions for z. The very last question is one that is, I probably can do it in 40 seconds. Let's see. Where's it gone? If I can find it. We have to prove this. Right, so we start by saying let z equal x plus iy, and the imaginary part of z is going to be y. So we start off with the left-hand side, substituting in, and we get x plus iy minus x minus iy. I'm out of time, but I think you'll find this one fine from the work solutions. Top line gives me this. It's a show that, so don't miss any steps, even if you've got 2 seconds left.